Welcome to Lecture 2.8, the Logistic Equation. So we actually mentioned this way back in, I think, the first lecture when we talked about population growth. Recall that the ODE for exponential growth looks like this, y prime equals ry. And a key property here is that this rate, r, is a constant. It does not depend on the actual population y of t. So here's a better model for the population growth. Let's suppose, as before, y of t is the population of a colony. Might be bacteria, might be rabbits, might be something else, who knows. When y of t is small, the population grows exponentially. This is what we talked about in the first lecture. I think I mentioned populations of bunnies. You have 2 bunnies, then 4 bunnies, then 8 bunnies, and 16, and so forth. It grows exponentially. However, when y of t is large, when population is close to the carrying capacity, it grows very slowly. It's like it decays to the value. Something like asymptotically, it'll approach the carrying capacity. And when y of t is too large, it decreases. So if the carrying capacity is up here, then y of t starts up here, it goes down like that. So this is also like a decay toward a value. So the big idea is when y of t is small, it grows exponentially, and when population is large, it decays. So the key point in all of this is that the rate r decreases as the population increases. So r is actually a function of, not of t, but of y. So what we had before, for standard exponential growth, well, up here, is if we were to plot the rate as a function of y, it would be constant. That's close to being almost supposed to be a horizontal line. Now what we have is if we were to plot the rate, it's going to be decreasing. So it's not clear whether it should be decreasing linearly or like this or something else. But the logistic model is a population model where this rate decreases linearly. So it's assumed to be a straight line. So to summarize, we have our differential equation is y prime of t is some rate which is now not constant, a function of y times y of t. So this is our differential equation, and instead of making this a constant, let's plug in some linear, let's say this is a function, a linear function in y. So if this is r right here, let's say that this has slope a, negative a, so let's write this as I don't want to say r of y equals r minus a times y. Okay? So in this example, let's check to make sure this works. Let's check 3 cases. When y equals 0, r of y equals our original rate r. And now we're going to assume that we're double using this r for a constant and for the function, but I think that's okay. So r is normal. When y is r over a, that's this point right here, r over a, then the growth rate is equal to 0, and that's good when y of t is large. Up here, population is large. It grows slowly or doesn't grow at all. This is actually going to be we're going to call this m for the carrying capacity. The carrying capacity is the population needed for the growth rate to be 0. It's the equilibrium population. And finally, when y is greater than r over a, then r of y is negative. In other words, when we are over here, when population is too big, the growth rate is negative and the population is shrinking. So we call this threshold I'm not going to write it down, I'm going to say the carrying capacity, m, and that's exactly what this m is right here. So let's rewrite our equation like this. So y prime equals r of y, we're going to write that as r minus a y times y. So this is called the logistic equation. Instead of r being constant, we assume it's linear. So let's simplify a little bit. And this will simplify as, let's see how I actually want to do this. Let's use this equation. I want to get rid of a, because a, here, this thing that I circled, m has meaning, it's the maximum, it's the carrying capacity. R has meaning, it's like the true exponential growth rate when the population is small, or I should say the limiting growth rate as the population goes to 0, and a is just the slope. A doesn't have much meaning here. So I'm going to write this as, so I'm going to eliminate a from this equation and write it in terms of the things that we understand, m and r. So a equals r over m, is that correct? Yeah, that looks right. So now this equation becomes r minus r over, let's see, r over m y times y. Now let's factor out an r. So I'm going to write this as y prime equals r times y times 1 minus, careful, y over m, and that's it. So this is the logistic equation. Let's say a couple things about it. The steady state solutions are 0. Well, remember the steady state solutions occur when y prime is 0, and that happens when y is 0 or this guy is 0. And this guy equals 0 either when, well, let's see, this is 0 when this is 1, which is when y, the population, is equal to the carrying capacity m. So to summarize, this differential equation is called the logistic equation, and the constant m represents the carrying capacity of the population. So the next thing to do, of course, is to solve this. And let's think about how we would solve this. So there's no t over here on the right-hand side. Well, there's y of t, but there's no variable t. So we can certainly separate variables. In other words, we can write this as dy over y times 1 minus y over m equals r dt, and then we can integrate both sides. And do you remember how to integrate something like this? Yep, it's partial fraction decomposition is what you need. You never thought that would come back, would you? Did you? Yeah, from Calculus 2, when you have something like this, you don't have a formula to integrate this, you need to break this up into partial fractions, and integrate each piece separately. It's going to be messy. It would probably take up 10 minutes in the entire space here, so I'm not going to do it. I'm just going to tell you what you get. So let's say use partial fractions. No big unhappy face here. You can use Wolfram Alpha if you want. Actually, not a bad thing to just pause this lecture right now, plug this into Wolfram Alpha, and see what it gives you. And in fact, that's what I'm going to do. So the solution is, if you were to solve this using partial fractions, is m over 1 plus c e to the negative rt. Now let's plot the solutions here. Remember, we learned how to do that in the first series of lectures, first section. There are two steady state solutions. So the steady state solutions are y of t equals, remember how to do this? Set this equal to 0 and solve for y. So if this is equal to 0, y, either that is 0, y is 0, or this term is 0, which happens when y is equal to m. Y equals m. So let's plot these. Let's say this is m. So we're going to have a steady state solution there, and we have a steady state solution along the y-axis at 0. Now, if the population, well, what we want is if the population is greater than m, then it, well, I'm not drawing this very well, then it approaches the carrying capacity from above, and if it's less than m, it approaches from below, something like this. And this is something, again, that we saw how to do in the first section. And so down here, the population is going to diverge and get negative. And remember how to check that? For each one of these regions, y prime is going to be constant. Not constant. It's going to have constant sign, sign. So if y is greater than m, if y is up here, then y prime is if y is bigger than m, then this term is negative. 1 minus something bigger than 1, that's negative, and that's positive. So y prime is negative in that case. I should probably use a different color. That's going to look bad. Y prime is 0, less than 0. In this region, y prime, if y is between 0 and m, that will be positive, that will be positive, so y prime is positive. And down here, y prime is negative, because both of these, that's going to be negative and that's going to be positive. Okay, so let me say a few obvious things about this. Initial population. Oh, let me use my pen. Initial population. Y of 0 equals, let's plug in t equals 0. We get m over 1 plus c. So it's tempting to say initial population is just c, but that's not correct. Is m over 1 plus c, and the limiting population is the limit as t goes to infinity of y of t. So let's plug in a really big number in for this. That's going to kill off this exponential, and we just get left with m over 1. So that's just going to be m. And that makes sense, that the population is going to approach m as time goes to infinity. Now, I should say a few things. Now, the limiting population, you may notice, is not m if we're down here, right? In fact, this function does not describe any of these curves because for this function, no matter what c is, as time goes to infinity, this gets killed off, and we approach m. So this is only going to describe so we have these extra curves in here that that we know from up here, but we don't see in here. And that should strike you as a little bit strange, and this may be a cop-out, but I'm going to say it's because this equation is nonlinear. When you have a linear differential equation, you have a nice one-parameter family of solutions. The general solution, something like this, and these are precisely all of the solutions, nothing more, nothing less. When you have nonlinear equations, you might have you might have multiple general solutions or none, or something weird can happen. So it might be a bit of a cop-out, but remember, we know the solutions look like this, or we know there are solutions that look like this mathematically from this equation, but when you solve it and you use partial fractions, you're only going to get some of the solutions. And in fact, you don't get the solution 0. Notice that? There's no value of c that's going to give you a solution of 0. And again, I'm going to say it's because it's nonlinear. But really what's happening, I guess a partial explanation is, remember back in algebra, if you wanted to solve x, solve x squared equals x. So what do? You divide through by x. You say, oh, let's divide both sides by x. And then you say, that just means x is 1. Well, what's the so what's the problem with that? Well, there's multiple problems. First of all, you're assuming that x is not 0, which it could be, and so when you're that's really the crux of it right there, is when you're doing this step, you're assuming that x is not equal to 0. And of course, x could be equal to 0. So when you do this step, you divide through by 0, and you can say, oh, you're just canceling both sides. You're assuming that you don't have this, and so you have to add that solution back in at the end, or x equals 0. Similar thing here in this process. Actually, you can see it right away. You're dividing by y and integrating. It better be the case that y is non-zero. Right away, if you're separating variables, you better say right away y is not equal to 0. Otherwise, you've just divided by 0 and the universe explodes. So that at least explains why you're missing the 0 solution from here. It doesn't quite explain why you're missing these, but again, for both of these, I'm going to say it's because nonlinear differential equations are not fun, or they're a lot more complicated. Let's do an example. Suppose we have a colony of bacteria that grows according to the logistic equation. The colony lives in a petri dish that can hold 50 grams. So right away that means that m is 50. Initially there are 10 grams. So that means that, well, I should say that we're going to use m of t for mass instead of y of t. So initially there are 10 grams. That means that little m of 0 is 10. And initially the mass is increasing at a rate of 1 gram per day. That does not mean that the constant r is equal to 1. That means that m prime of 0 is equal to 1. Find m of t. Okay, so let's write down the logistic equation. We don't have to, but it's going to make things easier. It's never a bad idea. Let's r times m times 1 over 50 over, no, that's not right either. I'm doing this off the top of my head, and m over 50. And remember, these m's you see here, these are lowercase m's for mass. This is m of t and m prime of t, not the same capital M that I have up here. Okay, so we know the solution to this. We know that m of t is 50 over 1 plus c e to the negative rt. So let's plug in the first initial condition. This is the simplest one because it involves plugging in 0 and not taking a derivative. So m of 0 is 50 over 1 plus c, and that equals 10. So 50 divided by 1 plus c equals 10. Some algebra in our head means that this better be 5, and so c better be 4. So c equals 4. And so now we have m of t equals 50 for 1 plus 4 e to the minus rt. Now we have two of these initial conditions, and we started with two unknowns, c and r. So if we use both of these, we should be able to get both c and r. And indeed, this first one got us c, and now we need to use this guy to figure out what r is. And there's several ways we can do this. The first thing that you might try would be take the derivative of this. So to use this, take the derivative. You can certainly do that. And plug in 0, set it equal to 1. And that will work. You can solve for r. It's going to involve a logarithm or something like that. But here's a better way. You don't need to do that. This equation here, this is the logistic equation. This holds for all time t. This is m prime of t. So you can think of this as m prime of t, m of t, and m of t. So I can certainly plug in t equals 0. In other words, m prime of 0 equals r times m of 0 times 1 minus m of 0 divided by 50. And now we can easily, we know all of these things, 10 and 1, so we can just solve for r. And that's actually really easy. So we get 1, that's this, m prime of 0 is 1, equals r times 10 times 1 minus 10 over, now let's just write it out, 10 over 50. And let's be very careful with fractions. It's easy to mess this up. So this is 1 equals r times 10 times, what is that, 4/5? 4/5. And so this thing is going to simplify to, that 10 over 5 is 2 times 4 is 8. So that's going to be 8r equals 1. So we get that r equals 1/8. And that may be a little surprising because you were probably expecting to get some sort of natural log thing here when you took the derivative and plugged in 0, set it equal to 1. There's an e there, but in fact I guess that's believable because you take the derivative and r comes out in front. When you plug in 0, the exponential goes away, so that you're not going to have to take a logarithm. Okay, so we are done. R is 1/2. So now the particulars, so the particular solution, and when I say particular solution, I'm always referencing something to this, I should say, to this initial value problem. Some people just say solution. I like saying particular. The particular solution to this initial value problem is m of t. So let's take our old solution of this guy and plug in negative or 1/8 for r. m of t equals 50 over 1 plus 4 e to the minus 1/8 t. There we go. And if you plot this, I have a little bit of room left. So this is m of t. This is 50. This is t. Then this is the solution that intersects the y-axis, or the m-axis, I guess, at 10. And it's going to look like this and go like this. And this is what it looks like, the solution, and this is what it is explicitly. And remember, to find that last step, to find r, we had two choices. We could have used our equation, which was easier, or we could have taken the derivative and then plugged this in. I want to finish this lecture with a neat topic. It's a more complicated equation than the logistic equation, though it's really just a simple extension of it, and it's called the threshold equation. And let me just ask the question, what happens if we were to replace r with negative r in the logistic equation? Well, in that case, so the answer is that we get an ODE. We get an ODE, and let me write it out. And I'm going to use capital T instead of capital M for my threshold, my maximum carrying capacity, and I'll explain why shortly. So now you would get y prime equals negative r times, it's the same thing, 1 minus y over m, which I'm going to call t now, times y. I guess before I put the y up in front, but it really doesn't matter. And so here I'm saying let t equal m. And the solutions are going to, let's think about what the solutions are going to look like. This is t, time t, and this is our threshold. So we're going to have the same steady state solutions, 0 and t, or 0 and m. That's not going to, the only thing that's going to change is the sign, the SIGN of the solutions. Instead of being like this, they're going to be like that. And instead of like this, they're going to be like this, and so forth. So in here, we have y prime is negative. Up here, y prime is positive, and here, y prime is negative. It's the opposite of what we had before. So our solutions are going to look like this. Going to be negative here. Oh, wait. Something is, I'm sorry, obviously, yeah. I should make this, they're going to be positive here. Positive. And then up here, they're going to be positive. Now this is not really going to model a population, with a carrying capacity m at all, right? Because I don't want to put m here because this is what's called an unstable equilibrium. So let me write that down. This is an unstable equilibrium. Equilibrium, and this is a stable equilibrium. Whereas for the logistic equation, everything was switched. This was stable, and this was unstable. So this actually models a population with an extinction threshold. Think of an endangered species. If you have a population, maybe of wild pandas or black rhinos in the wild, and it gets too low, then there's not enough of them to survive, and they will go extinct. So think of this as the extinction threshold. If a population is below that, then unless we intervene and take extra steps to save them, or to protect them, the population is going to go down to 0. And whereas if the population is above t, then it's gonna blossom and increase, in this case exponentially, though we know that's not realistic. And we don't need to worry about what happens when population is less than 0. So let me summarize that. There's this model's population with an extinction threshold. And that's why I wanted to call that t instead of m. And what I mean by this mathematically is if y of t is less than t, then the population dies out. And if y of t is greater than t, the population explodes. If you've been to Florida or know people in Florida, you may know that in the 80s or the 90s, alligators were supposedly endangered. And so when it was Save the Alligator campaigns, so they were potentially below this threshold or near it. And so people enacted measures to save the alligators, and now there's way too many of them, and they've just blown up and exploded. Well, some people will say there's too many. Okay, so as I said before, this is not realistic because we know that a population above the threshold is not going to grow exponentially. It's going to grow exponentially, and then it's going to die off. It's going to also have a maximum that, m should be up here. It's going to approach some maximum. So we would like a model that has both phenomena, that has both the extinction threshold and the carrying capacity. So we want a model with both phenomena, m and t. How about if I say that? Both phenomena, both carrying capacity and extinction threshold. So how do we do that? Let's just make one. Let's literally write down an ODE that has 3 steady states, 0, t, and m. So let's make one. So steady state solutions. So let's make steady state solutions. Y of t equals 0, t, and m. So I'm going to do this. I'm going to say y prime equals r times y times 1 minus y over m. So at this point, I have the logistic equation, right? So let's just add another term. 1 minus y over t. Look what I've done. This has 3 steady state solutions. How do we find that? Set y prime equal to 0 and solve for y. Well, this is 0 when either y is 0, y is equal to m, meaning this term is 0, or y is equal to t. So let's plot this. So this is t. Our threshold might be down here. This is capital T, and maybe our carrying capacity is up here. This is m, and this, of course, is y of t. So is this correct? Does this make sense? Let's check. Now we know that our solution curves should be y prime should be positive in this region, right? We want our solution curves to be going like this, not like this. Y prime should be negative down here. So we want our curves to go like that. And y prime should be negative up here. Y prime should be negative up in this region. Should go down like that. And let's check. Is that what this gives us? So when y prime is greater than m, then so when y prime is greater than m, this is positive, this is negative, and this is negative, because when y is greater than m, that's bigger than 1, and that's bigger than 1. So we have positive, positive, negative, negative, and that is wrong. So let's just add a negative sign right here. Now, when y is greater than m, we have negative, positive, negative, negative. That checks off. When y is between t and m, then this will be, let's see, this will be positive, this will be negative. Positive, negative, y prime is positive. And you can check the other regions as well. So when this happens, so this equation, we don't know how to, well, we do know how to solve it. You could do separation of variables. You could do partial fractions. I've never actually done this. I don't actually know what the solution that you would get would be, but I encourage you to do it. I'll encourage you to plug it into Wolfram Alpha. That shouldn't take long. And actually, when you do that, I'm actually not sure what you're going to get. I haven't done that before. I'm not sure if you're going to... Remember last time how we got only the positive solutions? We didn't get any of the negative ones. I don't actually know if our solution is going to give us all of these, or it's only going to give us, most likely, maybe either, I don't know, these or something like that. It's probably not going to give us all of the solutions. Certainly not the negative ones or the zero ones, but I don't know if it will actually give us all of these. But I encourage you to check it out. Maybe I'll put a homework problem on there. Okay, so this is something you could solve by separation of variables and partial fractions. We won't. But I'm just going to, I think it's worth showing you because it shows you a nice little extension of the logistic equation, how to just add this extra term on. And this model is called the threshold equation. It actually modeled the now extinct passenger pigeon quite well. Obviously, different population models, or different models fit different populations with varying degrees of success. And this one, let me write this down. This modeled the unfortunately now extinct passenger pigeon quite well.